Okay, let's start. Today we will talk about number and arithmetic. The number system used in the current computer system is binary. So we only have two symbols in the binary representation, 1 and 0, or true and false. They are base 2 because they are binary. So this is the basic representation of the current logic circuits and all digital computer systems are using the binary representation. So how can we convert a decimal number we use in daily life to the binary representation? I will present the algorithm. So this is a decimal number. It has 3 digits, 7, 3, and 6. Each number has its own position from the least significant bit, which is this bit, to the most significant bit. And we can write a number for each digital position, which is a 10 to 0, 10 to 1, 10 to 2. So this number indicates the base of that particular number position. For example, this is the least significant bit, this is the most significant bit, and this is the second bit. So each digit in that partition can be used as a multiplier for that particular base. So in this way, we can write the equation for this decimal number. So when you calculate this, you can get this number. By using the same algorithm, we can write the number for the other base, like base 2, binary, base 8, and base 16. Again, we need to write the base for each position like this, from 2 to 0 to 2 to 9. We have 10 digits here. Also from 8 to 0 to 8 to 3. So you can compare this equation against this one. The only difference between these two are the base here. This is base 10. This is base 8. Both of them will write the digit in the number position, like the multiplier here. By calculating this equation, you can get the decimal number of this base 8 number. This is the decimal value of this number, which is exactly the same as this number. So all the value for these three different basis number is a 637. When you see this symbol, it indicates base 8. When you see this this symbol, it indicates the hex of base 8, base 16 number. And here is one table to show the number represented by different bases. So we should be very familiar with the decimal number, just from 0 to 18. For binary number, we can only have two symbols, 0 or 1. How can we represent 2? We need 2 bits. And this is 18. In order to represent 18, we need 5 bits, like this. For base 8, we only have 8 symbol here from 0 to 7. If we want to write a 8 decimal 8 in the base 8, we have to write 1 0. So 1 0 in base 8 indicate a decimal 8. And then we have the base 16 here. We also have 16 symbols from 0 to F. F is 15. So if we want to have a decimal 16, we need to write 1 0 here. When you see 0B, it indicates this is a binary number. Again, another binary number. How to convert this binary number to this decimal number? This is a decimal number. If you see nothing in front of this number, it's a decimal number. How can we convert this binary number to the decimal number? We can use the equation here. We need to write 2 from 2 to 0, which is this bit. To 2 to 7. And write each digit in the bit position here. And then we can have this value. This is a base 8 number. This is a decimal number. How to convert this base 8 number to the decimal number? Again, we use the same algorithm too. The least significant bit is 820. The most significant bit is 2 to 1. And we have both 7 here. We write a 7 here and write another 7 here. And then we have a 63 here. So by the same equation and using different base, we can convert all the number in different bases to decimal number. So you can calculate these numbers yourself. The only difference is 16 to 0, 16 to 1, and 16 to 2. And then you can write these digits here. 1 multiply this, 0 multiply this, and 0 multiply this. Since these two are zeros, so the value will be this one, which is exactly the 256. This is how we can convert different number in different bases to the decimal number. And this slide indicates how to convert a decimal number to different bases. For example, how can we convert this value, decimal value, to its base 8 format of representations? We can use this conversion algorithm. In this conversion algorithm, we basically need to calculate the remainder. This value will be divided by this 8, which is the base we want. And then we can have the remainder. This is the result. This is the remainder. And we can continue to use this result to divide it by the base, which is 8. This is the result. This is the remainder. And we can write all the remainder here until the last bit. So the first remainder we get is the least significant bit. And the last one we have, the last remainder we have is the most significant bit. We can rewrite this number like this. Okay, this is the least significant bit, and this is the most significant bit. So a decimal number is equal to this base 8 number. So this so-called division and remainder calculation process is exactly the reverse process of this equation. It's exactly the reverse process of this equation. And here is another example how to convert this value to its binary representation. Because the binary representation base is 2, so we divided, this number will be divided by 2. And this is a result, and this is a remainder. We can continue to use the result to divide it by 2, result and the remainder, until we have this. So this is the least significant bit. This is the most significant bit. Eventually, this is the results. So how to convert the binary to base 8? This is simple. In order to do that, we just need to group the binary. 3 digits can be grouped into one group. So this is the 3 digits, another 3 digits, another 3 digits. Each group can be translated to a decimal number. For example, this is a 101, which is a 5. How can we know 101 is a 5? So we use the same equation, which is the least significant bit is 220, and then we have a 221, and then 222. So this is 101. 1. We have a 0 here, and we have a 1 here. This is 4 plus a 0 plus a 1, which is a 5. So how to convert a binary number to the base 8? We do the grouping first. Group 3 digits into one group and convert each group to a decimal number. This is the value of the base 8 number. How to convert a binary to hexadecimal? Basically, we follow the same algorithm, but use a larger group. We can group 4 digits into one group and convert each group into a decimal number. If a group has less than 4 digits, we can write another 20 here. So how to convert this one to the decimal? We write 220 to 223. And write a 1 here, a 1 here. Here is another 1, here is another 0. So we have a 8 here, plus 222, which is a 4, this one, and plus another 1. We have a 13 here, which is a D. Because A indicates 10, B is 11, C is 12 in hex, and D is 13. So this is the hex format of this binary number. This is the binary number, and this is the hex number. How can we do the arithmetic operation in binary? Basically, the addition works the same. No matter what base you try to add. For example, this is the base 10 hex number, which is 183 and 254. You just directly add them together. Because this is a base 10, so we can have a 7 here. 3 plus 4, which is a 7. 8 plus 5, which is a 13. So we have a carry here. This is a carry. And we write 3 here because this is 13. For the most significant bit, we have a 1 plus 2 plus another carry 1, which is a 4. And during the addition, we also need to propagate the carry. We just try to add the digits in each position. And we do not care about the base. For example, for the base 2, we can also directly do the addition. 0 plus 0, which is a 0. 1 plus 0, which is a 1. 1 plus 1, which is a 2. But this is a base 2. We cannot have a 2 here, so we have to write 2 as 1, 0. So the 0 can keep here, and the 1 can be proceed as the carry out for the higher bit, more significant bit. And then we can do the calculation like this. Basically, these two are the same, although the base are different. The only thing you need to be careful is that whether you can have a number in this base. For example, whether you can have a 2 here. The answer is no. Why? Because this is a base 2. In a base 2 number, you cannot have a 2 here. So a 2 have to be written into 1, 0. You have to have a carry out here and a 0 here. So this 2 is not right. This is the only thing you need to be careful during the addition. Actually, the computer used circuit to do the addition, and all that, basically all the addition are performed in base 2. So this is one example of the half adder. We have 2 inputs. Each input is only 1 bit. And we have a carry out. We have a sum here. Because we have 2 inputs, then the row, this is truth table. The row number is 222, which is 4. 0 plus 0, sum is 0, carry out is 0. 0 plus 1 is sum is 1, carry out is 0. 1 plus 0, the sum is 1, the carry out is 0. 1 plus 1, the sum is 0, carry out is 1. Because this is a 2 actually. This is the truth table. And we can use the canonical form and use the K-map, do the simplification for this truth table. Eventually, we can get the equation of the Boolean algebra for the sum and the carry out like this. This is an XOR operation. This is an add. This is an AND operation. We can use some gates to implement the sum and the carry out like this. This circuit indicator, if you have the XNOR gate, then the circuit will be very simple, just an AND gate and the XOR gate. This piece of circuit indicator, what if you do not have an XOR gate? You have to break the XOR gate down into 3 gates. No, actually 4 gates. NOT gate, actually 5 gates. Not one NOT gate indicate these 2 bars. And then the OR gate for this OR. And then another OR gate for this OR. And then the AND gate. I'm sorry, the AND gate for this AND gate for this AND. And then an OR gate for this one. So totally, there are 5 gates here, 2 NOT gate, 2 AND gate. Please notice that this is the AND gate, and the last one is an OR gate. This is what happens if you do not have an XOR gate. Which also means if you have a predefined XOR gate, your circuit can be significantly simplified. Actually, this is only a half adder. Half adder cannot be used as a component in the multi-bit adder. This is only 1-bit adder. When we try to build a multi-bit adder, we need to consider the carry in, not only the carry out, but also a carry in. For example, if this is an adder, my previous bit, my previous position, my less significant bit may give me a carry in. How can we handle this carry in? Then we need a carry in here. When we consider the carry in, we have 3 inputs. Then we have 8 rows here, which is a 2 to 3. You can finish this truth table yourself. And then you can grade the sum of the product, which we talk about the canonical form. We talk about it in the last lecture. We can do the simplification by either you use those laws or you can draw a K-map. Eventually, you can have the Boolean algebra for the carry out and for the carry and for the sum. So when we have the 1-bit full adder, we can build a multi-bit adder by connecting them together. Then this is the 4-bit adder. Each of this is a full adder. If you don't have a carry in here, you can always set this carry in to 0. But each bit will give you a sum here. And eventually it will give you a carry out here. So this is a complete adder, multi-bit adder. By this full adder, by this multiple bit full adder, we can handle all the addition operations. Next slide, we will talk about subtraction. When we talk about subtraction, we need to handle a negative number. So in order to indicate a negative number, we need to keep a digit for the negative number. So we keep the most significant bit as a signed bit for the negative or positive number. If it's a zero, then it's a positive number. If it's a 1, then this is a negative number. Then the absolute value of a number is actually decided by the other bits here, these 3 bits. These 3 bits are in base 2. When we convert them into decimal, it's a 7. So if the sign bit is 0, this is a positive 7. If the sign bit is 1, then it's a negative number. So originally by 4 bits, if we don't have the sign bit here, we have a 4 bits. We can use this 4 bits to represent from 0 to 15. But again, in order to indicate whether the value is negative or positive, we keep 1 bit as the signed bit. Now we can only represent from -7 to 7. We didn't reduce the range these 4 bits can represent. I think both of them can represent 16 number. But we just change the value of this 16 number. For the non-signed bit, the 16 number is from 0 to 15. But for the signed number, this is the -7 to +7. Both of them can represent 16 numbers. Some people may ask me, wait a second, you are talking about 16 numbers, but you know that from -7 to 7, we only have 15 numbers. How this happened? This is because we have 2 zeros in this case. What does 2 0 mean? Means 4 bits here. 4 bits here. If 4 bits are all 0, and of course this is 0. Even this is a signed bit. If the most significant bit is 0, then this is a so-called positive 0. If we write something like this, this is signed bit. This is signed number, and also this is another 0, because these 3 bits indicate as 0, and this bit indicates a sign which is a minus or negative 0. Both positive 0 and negative 0 are 0. They are equal. So the disadvantage of the signed bit is that we actually sacrifice, we reduce the range of a certain bit can represent. So in this way, these one can only represent 15. I'm sorry. Yes, this one can only represent 15 different numbers, But if we don't have the signed bit, we can represent 16. From 0 to 15, which is 16 numbers. Then we need to modify the encoding to solve these problems. So I talk about why we have 2 zeros here. A more advanced data encoding is so-called tooth complement representations. The tooth complement representations can solve this problem, can make us to only have 1 zero. In the tooth complements representation, the positive are not changed. If your signed bit is 0, then you can write the data just in its binary format. Again, if the signed bit is 1, then it's a negative number. To negative any number, we need to do multiple steps. The first one is invert all the bits, flip all the bits, and then plus a 1. I will give you multiple examples. For example, this is -1. First, we only write the digit, not the signed bit, but just the digits here. And then we write it into its binary form, which is all 0 and 1. We do the flip, which is the first step. The flip means all 0 will be changed to all 1s, and 1 will be changed to 0s. So this is 1, 1, 1, 3, 1, and 1, 0. The last step is a +1. So we use this number to represent -1. And let's do this calculation again for 8. For -8, we need to write 8 first. The binary form of 8 is 1, 3 zeros. We do the inversion. Now we have a 1, 0, 3 1s, and then add 1. So this is the 8, -8. And this is 0. So we write 0 here, inversion, and a +1, which is all 0. So now eventually we have the same representation for the 0. We only have 1 0. -0 is equivalent to the +0. This is good. And you should also notice that by 4 digits in the previous slides, we can only represent -7. But by the tooth complement, we can represent -8. This is the -8. So in this way, we can use 4 bits to represent 16 different numbers, 2. So you can do the calculation yourself. If this number is a positive number, you don't need to do anything. But if this number is a negative number, you do the flip and the addition, like this. This is a lookup table for you to look up what's the tooth complement for all 4 bits. This part is unsigned, so this is an unsigned number. We do not need to consider any negative number here. This is signed tooth complement. We have a negative number and then positive number. So this table indicates if I give you 4 binary digits, how can you convert the 4 binary digits to tooth complement representation and unsigned binary? For unsigned binary, it's simple. You can just use the equation we presented in the last several slides. For the two's complement, you need to do the flip and do the add one, and then you can get the correct value. So the signed two's complement have these advantages. We only have a 1, 0, and we can wrap from the largest positive to the largest negative. Negative are also leading, have leading ones. And then we present a table for you to look up unsigned bit and signed two's complement. Next one, we will talk about conversion. So if you have a number here, and this number is a two's complement number, if I give you more bits, can you keep the same value? For example, I give you 8 bits, another 4 bits to represent the same number. You cannot simply add zeros here. Otherwise, the value will be changed. If these bits are 0, then it's a positive number. You still need to plus more ones, insert more ones here to represent the same value. Again, if this is a positive number, you cannot insert ones here. You have to insert zeros here to represent the same value. So if you try to extending the number into a larger size number, you need to consider the signed bits. This is particularly true when you try to write some C code, try to do the shift operation. For example, right shift for this number. We have so-called logic shift, which is always insert zeros, or arithmetic shift, which is consider the signed bits. And this is how you can truncate a number into a smaller size. Again, when you do the truncate, you also need to consider the signed bit. For example, if you truncate this 15, which is of 8 bits to 4 bits, you also need to consider the signed bit. But sometimes you cannot because you don't have enough number of bits to do that. If you truncate 4 bits on this 15, the 15 will be converted to 1. Can you correct this error? The answer is no. Why? Because you don't have enough digits to represent 15. You cannot represent 15 by only 4 bits. This is so-called overflow. The overflow means you try to represent a very large number by a very small number of digits. So the number is too large, which is beyond the representation of those bits. When you do the extending, you cannot have overflow. If you are careful enough to look after the signed bit, you should be fine. No problem at all. But when you try to do the truncation, when you try to convert a large number, represent a large number by a smaller number of digits, you should be more careful because you can simply have some overflow problem. You can only detect the overflow, but you cannot solve that problem because no one can represent a very large number by a limited number of digits. after we have the 2's complement, good news is that we can do the subtraction. The subtraction can be done like this. We can rewrite the subtraction to a number plus a negative number. And the negative number can be represented by the 2's complement. This is a 2's complement number. And then we can do the addition. Just use the full adder we just built. Again, if we want to calculate 1 minus 3, we just calculate 1 plus a negative 3. And do the addition as normal. Let me give you one example. So if we want to do this one, we can use this table actually. The 7 can be represented by this one, 1000 plus. A negative 3 can be indicated by this number, 1101. 1 plus 1, which is 2. We write 1 and a carry here. This carry plus this one, which is also 2. Another carry here. We have a 3 ones here, then we have a 3. Then the sum is 1, the carry is 1. And for the last bit, which is 1 plus 1, which is 10. Because we only have 4 bits, we need to keep this. What's this value? This is a 4. This is a binary representation of this 4, which is exactly the value of this equation. So you can see that we just write the 2's complement number of these two numbers, decimal number, and do the addition directly. We can get the correct value here. But we need to be careful if we try to add 2 positive numbers and try to do a subtraction between 2 negative numbers. When we do this, we need to be careful. Why? I will give you one example. I just calculated this one. So 7 is a 0, 1, 1, 1. And 1 is a simple. 1 is just this one. 0, 0, 0, 1. When we do the calculation, 1 plus 1, which is a 1, 0, 2, carry in here. 1 plus 1, 0, 1. 1 plus 1, 0, 1. And then we have this one. The result is a 1 and 3 zeros. This number is weird. Why? Because the signed bit is a 0. The signed bit is 1, I'm sorry. But we just add 2 positive numbers. The sum of 2 positive numbers cannot be a negative number. Apparently, this one is incorrect. And you can see the previous addition we do. This signed bit is a 0. So this is a positive 4. And it seems that this is a negative 8. Which is wrong. Why we have this error here? This error is also overflow. The 8 is, we cannot represent 8 by 4 bits in 2's complement form. So if we try to represent too large or too small value by a very small number of digits, that's impossible. Overflow will happen. When the overflow will happen, when we try to add 2 positive number. In that case, we may be able to generate a very large positive number. That's when we will have overflow. And when we try to sum two negative numbers, we may be able to generate a very small negative number. In that case, we will also have overflow. But we cannot have an overflow when we try to add a positive number and a negative number. Why? Because if you can successfully represent that negative number and that positive number, the result of this one, the absolute value of the result of this one must smaller than these two. So if you can successfully represent this negative and positive number, the result should be also fine. We have enough bits to represent the result. We only need to be careful when we do these two. So in order to detect the overflow, we can create a piece of circuit, overflow detection. Then we need to understand how can we do that? How can we, when we will have the overflow? The overflow is always happened if the most significant bits carry in is not equal to the carry out. If we draw a truth table for the most significant bit, the overflow will happen in these two cases. How to detect whether they are the same or not? One simple XOR gate is enough. If they are different, this XOR gate will give you a 1. Otherwise, it always will be 0. So this is the summary of all we talk about today. We talk about number representations, 1-bit, 4-bit adders, negative numbers, and the two's complement numbers, addition, how to detect the overflow, how to do the subtraction. The last two slides indicate how can we convert a normal multiple bit full adder to a adder which can support subtraction operation. We need to add some extra circuits. For example, the NOT gate. We add the a NOT gate for each bit for the second operand, which is a B. All the bits of the second operand. What's the inverter for? The inverter is for the flip in the two's complement. When we try to convert a number to its two's complement, we need to do the flip. First, flip all the bits and do an addition. So we can use this carry in. This is the add 1, okay? Eventually, we can reuse this least significant bit carry in. We always set this value to 1 if we want to perform a subtraction. Besides this, we also need to add all the NOT gate here to do the flip. So by doing all these, we can have a subtractor here. So this is subtractor, not an adder, because no matter you want or not, we always do the we convert a number to its complement first. So by some control logic, we can switch this piece of circuit between the adder and the subtractor by adding some mux. The input of these mux is the inversion and the normal value of the B. If we want to do the addition, we just use the normal value. Otherwise, if we want to do a subtraction, we do the inversion, select the NOT value here. And also, if this is the normal addition, the carry in of the least significant bit is 0. Otherwise, if we want to do a subtraction, we need to convert it to the 2's complement. We need to add 1 here. So the subtraction is represented by the 1. And this 1 can go to the carry in of the least significant bit. And this one also is the control bit of the mask. If it is set to 1, then the mask will output the not value here. All the not value will go through this mask and get into the adders. The last step is the overflow. We need to evaluate whether the carry in and carry out for the most significant bit are the same or not. If they are different, then you may have the overflow. I will assign some homework for you to understand the 2's complement and addition and subtraction better. If you have any question, you can ask now, or you can write an email to me. Any question? If no question, we can stop today. Thank you very much.
Thanks.
One question.